What if everything you see in the night sky, every shimmering star, every distant galaxy, is just a tiny stitch in the universe's grandest tapestry? Hidden in the darkness between them lies an architecture so vast, so intricate, that it defies human scale. This is the cosmic web, a sprawling network of invisible threads tying galaxies together across billions of light years. But here's what no telescope can show you. These connections aren't just celestial landmarks. They're active highways where galaxies exchange matter, energy, and even their fates. Some threads hum with star-forming factories, while others stretch into voids so empty they challenge our very definition of space. Why should you care? Because this web isn't just out there, it's the reason you exist. The same forces that sculpted galaxies also delivered the ingredients for planets, oceans, and life itself. So let's trace these cosmic threads together, from the faintest tendrils to the most massive knots, and uncover how the universe built its masterpiece one gravitational handshake at a time. Picture a structure so enormous that it would take light, the fastest thing in the universe, over 500 million years just to cross it. This is the Great Wall of Galaxies, a staggering filament of superclusters so vast it redefines what we thought possible in the cosmos. Imagine galaxies, each home to billions of stars strung together like beads on an invisible thread, forming a celestial spine stretching across the darkness. When astronomers first discovered this megastructure in 1989, it shattered expectations. Before then, most assumed matter was scattered evenly throughout space. But the Great Wall revealed something extraordinary, a hidden architecture woven together by gravity over billions of years. Dark matter, that mysterious substance we can't see but whose pull shapes everything, acts like cosmic glue, binding galaxies into these immense ribbons. Even more fascinating, the Great Wall isn't alone. The Sloan Great Wall, discovered years later, dwarfs even this colossus, proving that these formations aren't rare flukes, they're part of the universe's blueprint. And if we've found two, how many more lie beyond our current view? The question lingers, teasing the possibility that we've only just begun to map the true scale of the cosmic web. What's truly humbling is the role these structures play in our own existence. The same gravitational forces that shaped these walls also guided the raw materials that would one day become stars, planets, and eventually us. So when you gaze at the night sky, remember, you're not just looking at scattered stars, you're glimpsing the threads of a tapestry far grander than we ever imagined. But how does something invisible hold the entire universe together? Meet dark matter, the cosmic web's mysterious scaffolding. Think of it like this. If galaxies were glowing lanterns, dark matter would be the unseen wires keeping them suspended in place. We can't see it, touch it, or even directly detect it, yet without its gravitational grip, galaxies would spin apart like untied balloons in the wind. Astronomers first stumbled onto dark matter's existence back in the 1930s. Noticing stars on the edges of galaxies moved far too fast for the visible matter alone to hold them. Something unseen had to be anchoring them, something with mass but no light. Today, supercomputer simulations like the Millennium Run show dark matter's ghostly influence in stunning detail. Billions of particles, governed only by gravity, slowly clump together over cosmic time, forming vast filamentary highways where galaxies later gather like dew on a spider's web. The irony, this invisible architect shapes everything we can see. The Milky Way sits nestled in a dark matter halo and the cosmic web's grandest threads. They trace the densest rivers of this shadowy substance, yet despite its obvious role, dark matter remains stubbornly elusive. Is it made of theoretical particles like actions or WIMP? Or something even stranger? Every experiment from deep underground labs to space telescopes brings us closer to an answer. Here's what we do know. dark matter doesn't just connect galaxies, it predestines them. The same gravitational wells it carved billions of years ago dictated where stars would ignite and life could one day emerge. So while it hides from our telescopes, its fingerprints are everywhere. The cosmic web doesn't just hang in space, it's held together by the universe's best-kept secret. Galaxies don't drift through the cosmos alone, they travel in rivers. Not of water, but of starlight, gas, and dark matter, streaming along vast filaments that weave the universe together like threads in a spider's web. These galactic highways stretch mind-bending distances, some longer than 500 million light-years, connecting clusters and superclusters in an intricate dance orchestrated by gravity. Take the Pisces-Cetus supercluster complex, an almost unimaginable structure binding thousands of galaxies along a single filament. Picture it as a celestial freeway, with galaxies moving steadily along lanes carved by dark matter's unseen pull. But unlike highways on Earth, these routes don't just carry traffic, they create it. As gas funnels along these filaments, it pools into dense pockets, igniting bursts of star formation and birthing new galaxies along the way. Why do galaxies follow these paths so precisely? It all comes down to gravity's relentless pull. In the early universe, tiny ripples in matter, seeded by the Big Bang, slowly grew under their own weight. Dark matter's tendrils formed first, drawing in gas and galaxies like cosmic rivers gathering tributaries. Over billions of years, these rivers became the universe's largest structures, with galaxies lining up like beads on a string. But the real magic happens where filaments cross. These intersections are the universe's busiest hubs, cosmic cities where galaxies collide, merge, and trigger unimaginably violent bursts of star formation. Some of the most massive galaxy clusters we've ever found sit at these junctions, growing fat on the constant flow of matter. And just like cities shape the fate of the people within them, these hubs determine the destiny of entire galaxies. What's astonishing is that this same process, filaments feeding galaxies, may have set the stage for our own existence. The Milky Way likely formed along one of these threads, its stars and planets built from gas delivered by the cosmic web. So when you look up at the night sky, remember, you're not just seeing scattered stars, you're witnessing the remnants of ancient highways that built everything we know. Far from the bustling highways of galactic filaments, the universe holds its emptiest secrets, vast cosmic voids where galaxies are almost strangers. These are not just blank spots on the map, but staggering deserts of space, some so large they could swallow thousands of Milky Ways whole. The Boötes Void, one of the most famous, stretches an astonishing 330 million light-years across, a yawning emptiness where you'd expect to find tens of thousands of galaxies, yet fewer than 60 have been spotted. So how did these voids form? Rewind to the early universe when matter wasn't spread evenly. Tiny density fluctuations like ripples in a pond determined where galaxies would one day thrive. Where matter pooled, filaments grew, feeding galaxies. Where it was sparse, gravity pulled what little there was toward the denser threads, leaving behind these gaping hollows. It's as if the cosmos took a deep breath and forgot to exhale in certain places. But here's the twist: voids aren't completely barren. A handful of lone galaxies cling to existence here like desert oases in the stars. Astronomers call them void galaxies, and they're some of the most isolated objects in existence. Without neighbors to influence them, these rebels evolved differently, often smaller, bluer, and hungrier for gas than their crowded counterparts. Studying them is like finding life in Earth's harshest environments. They show us how galaxies adapt when stripped of everything familiar. What's truly humbling is realizing these voids aren't just empty space, they're active players in the cosmic web. Their lack of mass creates a gravitational push, subtly repelling galaxies and shaping the web's expansion. In a way, they're the universe's negative space, defining the structure of everything we see by what isn't there. So next time you gaze up at the night sky, remember between the stars and galaxies, there's an echoing quiet, a reminder that even absence can shape the cosmos. At the bustling crossroads of the cosmic web, where filaments intersect like celestial thoroughfares, something extraordinary happens. Here, galaxies don't just pass by, they settle, collide, and form sprawling metropolises on a scale so vast it's almost beyond comprehension. These are galaxy clusters, the universe's grandest gatherings of matter, where thousands of galaxies crowd together in a gravitational dance, bound by invisible threads of dark matter. Take the Coma cluster, for example, an immense city of over 1,000 galaxies, each one a swirling island of stars. But unlike the serene galaxies we often picture, this cluster is a place of chaos. Galaxies whip past one another at breakneck speeds, their mutual gravity distorting their shapes into long, twisted streaks. The space between them isn't empty either, it's filled with a superheated gas, reaching temperatures of millions of degrees, glowing so intensely it emits X-rays visible to telescopes. And the deeper we look, the stranger it gets. These clusters don't just exist passively, they reshape the fabric of space itself. Their immense mass warps space-time so dramatically that light from distant galaxies behind them bends, creating natural magnifying glasses we call gravitational lenses. Thanks to this effect, astronomers can glimpse objects otherwise too faint to see, like cosmic zoom lenses gifted by the universe. But the real power lies at the very center of these clusters, where supermassive black holes lurk, some billions of times the mass of our Sun. These behemoths don't just sit idle, they feast on surrounding gas, spewing out jets of energy so powerful they can stoke or stifle star formation across entire galaxies. They're the ultimate anchors, regulating the frenzied life of the cluster like cosmic conductors. What's astonishing is that these clusters aren't static. They grow over time, pulling in new galaxies like a metropolis expanding its borders. And just as cities shape the lives of those within them, these clusters dictate the fate of their galaxies, merging them, reshaping them, even stripping away their gas in violent encounters. Yet without them, the cosmic web would lack its richest, most dynamic hubs. So when we gaze into the heart of a galaxy cluster, we're not just seeing a snapshot of deep space, we're witnessing the universe's most vibrant communities, where gravity writes the rules and black holes reign supreme. Some of the greatest discoveries in science begin with numbers that stubbornly refuse to agree, and right now, the universe is giving us one of its most perplexing mismatches. Meet the Hubble Tension, a cosmic contradiction where two of our most trusted methods for measuring the universe's expansion rate deliver shockingly different answers. It's as if the cosmic web itself is whispering a secret we haven't quite decoded yet. Here's the puzzle. When astronomers study the ripples in the afterglow of the Big Bang, the cosmic microwave background, they calculate an expansion rate of about 67 kilometers per second per megaparsec. But when they measure how fast galaxies are racing apart today, using supernova and stars as cosmic mile markers, the number jumps to 73. That gap might seem small, but in a universe governed by precise physics, it's like stepping on a scale and getting two weights that can't both be true. What's causing the discrepancy? Theories abound. Maybe dark energy, the mysterious force accelerating cosmic expansion, isn't constant but grows stronger over time. Or perhaps the cosmic web's uneven structure is skewing our measurements, with dense filaments and empty voids tugging galaxies in ways we haven't fully accounted for. There's even a wild card. Could undiscovered particles or forces be subtly reshaping spacetime itself? Enter the James Webb Space Telescope, our newest cosmic detective. With its razor-sharp vision, JWST is peering deeper into the cosmic web than ever before, scrutinizing distant galaxies and the space between them for clues. Early observations already suggest the Webb's scaffolding might be more complex than we thought, with voids stretching wider and filaments woven tighter in certain regions, subtle variations that could throw off our cosmic speedometer. But here's the thrilling part: whatever the answer, this tension isn't just a problem to solve, it's a doorway. If dark energy is changing, it rewrites our understanding of the universe's fate. If the Webb structure hides new physics, it means we've barely scratched the surface of how spacetime truly behaves. One thing's certain: the cosmic web isn't just connecting galaxies. It's revealing cracks in our cosmic knowledge, and through them we might glimpse truths far stranger than we ever imagined. We've traced the cosmic web's filaments and voids, but zoom out even further and you'll find something astonishing. The Milky Way isn't just drifting. It's part of a colossal current swept along in a river of galaxies toward a hidden gravitational beacon. This is Laniakea, our home supercluster, a name from Hawaiian meaning immeasurable heaven. Stretching over 520 million light-years and binding 100,000 galaxies, it's not just a structure, it's a movement. At its heart lies one of cosmology's great mysteries, the Great Attractor. Imagine a cosmic whirlpool, its gravity so intense that everything in Laniakea, our Milky Way included, flows toward it at nearly 2 million miles per hour. For decades, astronomers struggled to see what was pulling us. Dust and stars from our own galaxy's disk obscured the view, like trying to spot a lighthouse through fog. But recent X-ray and radio observations peeled back the veil, revealing a dense knot of galaxy clusters near the Norma cluster, their combined mass warping spacetime itself. Yet the Great Attractor isn't the end of the journey. Laniakea itself is in motion, drawn toward an even larger congregation of mass nicknamed the Shapley Supercluster. It's a reminder that gravity's reach never truly ends, just scales up, weaving superclusters into filaments, filaments into walls in an infinite fractal dance. What does this mean for us? Laniakea is more than a map, it's a time capsule. The way galaxies flow within it preserves clues about the universe's raw ingredients and how gravity sculpted them over billions of years. Even our Milky Way story, its collisions, starbursts, and quiet periods, was shaped by this supercluster's tides. So next time you feel grounded, remember, you're riding a galaxy adrift in an immeasurable heaven, caught in a current older than Earth itself. The cosmic web doesn't just connect places, it tells us where we're going. The faintest glow in the universe holds the sharpest snapshot of creation. Stretching across the entire sky, the cosmic microwave background isn't just leftover heat from the Big Bang, it's a fossilized imprint of the cosmic web's very first threads. Picture this, a baby universe just 380,000 years old, hot and dense as molten steel. As it finally cools enough for light to break free, that first burst of radiation carries with it a secret, the exact blueprint for everything that would follow. When the European Space Agency's Planck mission mapped this ancient light in exquisite detail, it didn't just see a uniform glow. Hidden within were tiny temperature differences, fractions of a degree, where some patches of the young universe were ever so slightly denser than others. These microscopic ripples might seem insignificant, but they were destiny written in heat. Over billions of years, gravity amplified those subtle imbalances, pulling matter into the filaments and voids we recognize today. The densest spots became galaxy clusters, the emptiest regions stretched into cosmic voids. But here's the mystery: why is the CMB so astonishingly smooth overall? The answer lies in cosmic inflation, a split second after the Big Bang, when the universe expanded faster than light itself. This violent stretching ironed out most wrinkles, leaving only the faintest variations behind. Without inflation, those delicate ripples might never have grown into the web we know. What's truly tantalizing are the deeper patterns we haven't yet decoded. Some theorists believe the CMB could hide evidence of parallel universes or exotic physics from the universe's first moments. Others think it might reveal how dark matter, already shaping those early density fluctuations, behaved when everything was just a searing plasma. For now, the CMB remains our clearest window into the cosmic web's origins. Those faint temperature variations, they're not just relics. They're the universe's first whispers telling gravity where to build. And the stunning part, without those ancient blueprints, neither galaxies nor the spaces between them would exist, and neither would we. So when you hear static on an old radio, remember, some of that noise is the echo of creation itself, still humming the song that shaped the cosmos. Galaxies may look serene from a distance, but the cosmic web turns them into predators. Across the universe, these island universes don't just drift. They consume one another in gravitational duels that reshape the cosmos. Galactic cannibalism isn't rare. It's how the universe builds its grandest structures. Take the Tadpole Galaxy, a stunning example of a recent cosmic meal. Its long, shimmering tail, stretching nearly 280,000 light-years, isn't just for show. That's a trail of stars ripped loose during a violent encounter, like crumbs scattered from a celestial feast. These mergers aren't quick events either. They unfold over hundreds of millions of years as gravity tangles two galaxies into one, twisting their spirals, flinging stars into new orbits, and igniting bursts of star formation in the chaos. Our own Milky Way is no stranger to this process. It's already swallowed dozens of smaller galaxies, leaving behind ghostly streams of stars as evidence. And in about 4 billion years, it'll face its biggest challenge yet, a head-on collision with the Andromeda Galaxy. When that happens, the two spirals will merge into a single, enormous elliptical galaxy, their stars rearranged but unharmed. After all, galaxies are mostly empty space, so actual stellar collisions are rare. But the gas clouds, that's where the fireworks happen. Mergers supercharge star birth by compressing vast reservoirs of gas, triggering supernova and lighting up galactic centers. Some of the brightest galaxies we see, like the antennae galaxies mid-collision, are veritable stellar nurseries, churning out new stars at rates dwarfing our galaxy's quiet pace. Yet for all their violence, these events are creative acts. The cosmic web doesn't just connect galaxies, it feeds them to one another, recycling matter into new forms. What's truly humbling is realizing these mergers don't just alter galaxies, they rewrite the web itself. Every collision sends ripples through dark matter filaments, redistributing mass and altering the gravity map of the universe. The web isn't static, it's a living network constantly rewiring itself through these encounters. So when you gaze at a galaxy, remember, you're not just seeing an isolated island of stars. You're witnessing a survivor in an endless cosmic dance where gravity is both the choreographer and the feast. Some of the universe's most important secrets aren't hiding in distant galaxies. They're lingering in the spaces between them, so faint we almost miss them entirely. Astronomers call this the missing Baryon problem, and it's one of cosmology's greatest detective stories. Here's the puzzle: when scientists tally up all the normal matter, the stuff that makes up stars, planets, and us, roughly half of it has vanished without a trace. But the cosmic web never truly loses anything. It just hides matter in plain sight. The culprit, a ghostly ocean of superheated gas known as the warm-hot intergalactic medium, or WIM. Picture steam so thin it's invisible, but so vast it forms a fog spanning billions of light years, clinging to the cosmic web's filaments like dew on a spider's silk. This isn't just any gas. It's been heated to millions of degrees by shockwaves from colliding galaxies and exploding stars, making it too energetic to form stars but too diffused to glow brightly. For decades, the WIM eluded every telescope. It doesn't emit visible light, and its X-ray signature is whisper faint. But astronomers have a trick: quasars. These brilliant beacons, powered by voracious black holes, shine like cosmic lighthouses through the WIM tendrils. As their light travels to us, the gas absorbs specific wavelengths, leaving behind faint chemical fingerprints. It's like finding water in the desert by tracking where the sunlight dims as it passes through unseen vapor. Now, tools like the E-Rosetta telescope are turning these clues into a map. By stitching together thousands of quasar observations, they've begun tracing the WIM delicate threads, confirming that the missing baryons were here all along, woven into the cosmic web's fabric. Why does this matter? Because without this hidden reservoir, the universe's ledger doesn't balance. The same gas that's hiding today may have once fueled galaxy formation, and it could still be cycling back into new stars. The WIM isn't just filling gaps in our models, it's completing the story of how matter flows across the cosmos. So while we once stared at the voids between galaxies and saw nothing, we now know better. Those spaces are teeming with the universe's quietest, most essential ingredient. Deep in the cosmic dawn, when the universe was barely 1 billion years old, something extraordinary flared to life, beacons so bright they outshone entire galaxies. These weren't stars or supernova, but quasars, the raging hearts of young galaxies, powered by supermassive black holes feasting on staggering amounts of gas. Picture a lighthouse not on a rocky coast, but adrift in the early cosmic web, its beam cutting through the primordial darkness to illuminate the very threads of creation. What makes quasars so special isn't just their brilliance, it's what their light passes through on its journey to us. As these beams travel billions of light years, they pierce the faint tendrils of gas weaving through the cosmic web. Like sunlight filtering through stained glass, the light absorbs certain wavelengths, leaving behind a chemical fingerprint. Astronomers decode these signatures to map where gas clustered in the ancient universe, revealing how the web's skeleton looked long before today's grand filaments took shape. But why did quasars burn so fiercely back then? The answer lies in the chaos of the early cosmos. Fresh galaxies were gas-rich, their central black holes gorging on abundant fuel. As matter spiraled inward, friction heated it to millions of degrees, creating disks so luminous they dwarfed every star in their galaxy combined. Yet this frenzy couldn't last forever. Over time, black holes either devoured their nearby gas or blasted it away with powerful jets, dimming their brilliance. Today, most quasars sleep their fiery youth preserved only in the light still traveling across the ages. Here's the twist: quasars didn't just light up the early universe, they helped build it. Their intense radiation ionized surrounding gas, shaping how galaxies formed. Their outflows seeded heavy elements into the web, enriching future stars, and their flickering patterns, they're like cosmic hourglasses, letting us measure the universe's expansion with staggering precision. So when we catch a quasar's glimmer in our telescopes, we're not just seeing a distant beacon. We're glimpsing a flashbulb moment from the cosmic web's childhood, one that reveals how the universe grew from a tangled skein of gas into the ordered vastness we call home. Hidden beneath the cosmic web's grand tapestry, another invisible force is quietly at work, one that doesn't just connect galaxies but steers them. Imagine an unseen network of magnetic fields, woven through the universe's largest filaments like fine threads of iron in silk. These forces are too faint to see, yet their pull shapes how gas moves, stars form, and galaxies evolve. For decades, astronomers thought magnetism was a footnote in cosmic history. Now, new discoveries suggest it might be a hidden architect of the web itself. The mystery begins with a simple question: where did these magnetic fields come from? One theory points to the universe's fiery infancy. In the chaos after the Big Bang, swirling plasmas could have generated weak magnetic seeds, stretched and amplified over billions of years as galaxies formed. Others argue the fields were forged later, sparked by violent dynamos inside galaxy clusters, where superheated gas and black hole jets churned like cosmic generators. Enter ALMA, the Atacama Large Millimeter Array perched high in Chile's desert. By studying polarized light from distant galaxies, ALMA has done the impossible, mapped magnetic fields along the cosmic web's faintest tendrils. The shock, they're up to 1 million times stronger than predicted, tangled into braids that stretch for millions of light years. Even more surprising, these fields align with the web's filaments, as though gravity and magnetism worked in tandem to sculpt the universe's structure. So what does this mean for galaxies riding these magnetic rivers? Picture a vast, invisible highway where charged particles surf along field lines, guiding gas into galactic hubs or diverting it into voids. Some theorists believe these forces could even solve a long-standing puzzle: why galaxies at the web's nodes grow so massive so quickly. Magnetic fields might act like cosmic conveyor belts, funneling extra gas into their cores. Yet the biggest revelation is how little we still know. If magnetism truly binds the cosmic web, it challenges our models of galaxy formation, adding a layer of complexity to gravity's solo act. ALMA data is just the first clue in a much larger story, one where the universe's grand design may depend as much on invisible fields as on the pull of dark matter. So the next time you gaze at the stars, remember there's more shaping their paths than meets the eye. The universe has built its grandest structures over billions of years, but now an invisible force threatens to unravel them all. Dark energy, the mysterious phenomenon accelerating cosmic expansion, isn't just stretching space, it's rewriting the fate of the cosmic web itself. Think of it like this: gravity has spent eons weaving galaxies into filaments and clusters, while dark energy tugs in the opposite direction, pulling the fabric of reality apart at the seams. For now, gravity still holds sway in dense regions like Laniakea, where thousands of galaxies remain bound together, but peer far enough into the future and the balance could tip. If dark energy's strength grows over time, a scenario some models predict it might eventually overpower even the strongest gravitational bonds. The result? A chilling possibility cosmologists call the Big Rip. In this scenario, expansion grows so violent that galaxy clusters, then individual galaxies, then stars themselves would be torn from one another. In the final moments, even atoms and subatomic particles could be shredded apart by the sheer force of stretching space-time. But here's the twist: not all hope is lost. Some theories suggest dark energy's influence might plateau or even fade, leaving the cosmic web's largest structures intact. Superclusters like Laniakea could endure as cosmic islands, their galaxies huddled together in an otherwise empty, ever-cooling universe. The deciding factor lies in dark energy's true nature, something we've yet to fully grasp. What's certain is that the cosmic web isn't static. Right now, telescopes like Euclid and the Dark Energy Survey are mapping how galaxies move with unprecedented precision, searching for clues in the subtle war between gravity's pull and dark energy's push. Every measurement brings us closer to answering whether the web will fade into isolation or cling together against the tide. So while the universe's fate remains uncertain, one thing is clear: the story of the cosmic web isn't just about how it formed, but how it might one day end. And in that tension between connection and dissolution, we're not just observers. We're temporary participants living in the brief era when the web's glory is still visible and its mysteries are within our reach. Here's your next segment, crafted to flow seamlessly while introducing fresh insights on the local void. Most of us never think about the empty spaces in the universe until we realize we're floating right next to one. Just beyond the Milky Way's bustling spiral arms lies a staggering nothingness, the local void. This cosmic desert stretches 150 million light-years across, a yawning gap where galaxies are almost strangers. And its emptiness isn't just a curiosity, it's actively pushing us. For decades, astronomers puzzled over why our galaxy moves so fast relative to the cosmic microwave background. The answer: we're caught in a gravitational tug-of-war. While the great attractor pulls us forward, the local void shoves from behind. With so little matter in its expanse, the void's weak gravity creates a kind of negative pressure, repelling nearby galaxies like a cosmic undertow. Yet the local void isn't entirely barren. A handful of isolated galaxies cling to its edges, including the oddball galaxy NGC 6520, nicknamed the loneliest galaxy for its solitary position. These renegades evolve unlike their crowded counterparts, often smaller, bluer, and hungrier for gas. Studying them is like finding life in Earth's deepest ocean trenches. They reveal how galaxies adapt when stripped of neighbors. Here's what's really thought-provoking. Voids like this might be the universe's unsung architects. Their emptiness isn't passive, it sculpts the cosmic web by redirecting galactic flows. Simulations show that without voids, filaments wouldn't stretch as sharply, and clusters might not form as densely. The local void, then, isn't just our quiet neighbor. It's a silent partner in shaping everything we see. So the next time you gaze at the Milky Way's starry band, remember, we're not just inhabitants of a galaxy. We're travelers on a raft drifting between the cosmic web's great rivers and its emptiest seas, and that journey, it's far from over. The universe doesn't build stars haphazardly, it follows a recipe written in gravity and gas. Across the cosmic web, invisible filaments act like celestial conveyor belts, channeling raw hydrogen into galaxies where it ignites into stellar fire. These rivers of gas don't just trickle in, they surge, collide, and collapse under their own weight, sparking chain reactions that light up the darkness. Take the bones of the Milky Way, a network of dense, cold filaments snaking through our galaxy like cosmic scaffolding. These structures, some stretching hundreds of light-years, are star factories in the making. When gravity shrinks them into tight knots, the gas within becomes so pressurized it flares to life, birthing clusters of stars at once. It's a scaled-down version of what happens across the universe, where the web's largest filaments funnel fuel into galactic hubs on a mind-bending scale. But why does this delivery system matter? Without it, galaxies would starve. The gas floating in voids is too sparse to ignite stars on its own. It's only when filaments concentrate it, like rainwater gathering in river valleys, that conditions become ripe for creation. Some of the most prolific stellar nurseries, like the Orion Nebula, owe their brilliance to these inflows. Even our Sun likely owes its existence to a long-ago infusion of gas from the web's tangled streams. The real magic happens at the intersections. Where filaments cross, gas piles up into dense hubs, triggering starbursts so intense they outshine entire galaxies. The Spiderweb Galaxy, for instance, sits at a filament crossroads, churning out stars 1,000 times faster than the Milky Way. Yet for all their fury, these events aren't chaotic. They're orchestrated by the web's elegant structure, turning the universe's emptiest regions into silent suppliers of life's ingredients. What's humbling is realizing this process never stops. Even now, fresh gas seeps into galaxies along these invisible highways, ensuring new stars will blaze long after old ones fade. The cosmic web isn't just a map of where things are, it's a blueprint for how the universe keeps reinventing itself, one spark at a time. Imagine looking out your window and realizing your house sits at the center of an invisible bubble, one so vast it could swallow 2,000 Milky Ways lined up end to end. That's the startling claim behind the KBC Void. a hypothetical cosmic emptiness some scientists believe might envelop our entire galactic neighborhood. At an estimated 2 billion light-years wide, this would be the largest void ever discovered, and its existence could upend how we measure the universe itself. The controversy started with a simple mismatch. When astronomers calculate how fast the cosmos is expanding, they get different answers depending on whether they study nearby galaxies or the distant cosmic microwave background. One possible explanation: if we're floating inside an enormous underdense region, the lack of surrounding gravity would make our local galaxies appear to be fleeing faster than they truly are, like runners on a treadmill set at a slight incline. But here's where it gets thorny. The KBC Void would dwarf even the largest known voids by a factor of 10, defying standard models of cosmic structure. Critics argue such a colossal emptiness is statistically improbable, like finding a soccer field-sized hole in an otherwise tightly woven quilt. Yet supporters point to peculiarities in galaxy surveys. Our local universe does seem sparser than expected, with fewer massive clusters and more gaps than simulations predict. What's at stake isn't just a record-breaking void. If the KBC Void exists, it means our cosmic address isn't average. We're perched in a rare, quiet corner of the web, skewing our measurements of dark energy and the universe's fate. Alternatively, its sheer size might hint at gaps in our understanding of inflation or dark matter's behavior. Either way, the debate forces us to confront a humbling possibility. After centuries of mapping the heavens, we might still not know what normal space looks like. As telescopes like LSST begin mapping billions of galaxies in unprecedented detail, we're closing in on an answer. Whether the KBC Void is confirmed or debunked, its legacy is already reshaping cosmology. Sometimes the most profound discoveries begin not by finding something, but by questioning why we seem to be missing so much. Somewhere beyond the edge of all known galaxies, an invisible river tugs at the cosmic web, not from within, but from outside our observable universe. This is the dark flow, one of cosmology's strangest enigmas, where entire galaxy clusters seem to drift in unison toward some unseen horizon, as if the universe itself is tilting toward a hidden weight. It all began with NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, which in 2008 detected something unsettling. By tracking the motion of galaxy clusters through the cosmic microwave background's subtle temperature shifts, scientists noticed clusters weren't just moving randomly, they were streaming together at breakneck speeds, up to 2 million miles per hour, toward a single patch of sky. The kicker: there's nothing massive enough in that direction to explain the pull. Theories abound, but each stretches our understanding of reality. Some suggest the flow could be the gravitational fingerprint of another cosmic web, an entirely separate universe bubble brushing against ours in the multiverse. Others propose it's an ancient relic from before the Big Bang, a scar left by quantum fluctuations in whatever cosmic landscape existed prior to inflation. The most radical idea, that our observable universe is just a pocket of something far grander, and the dark flow is gravity leaking in from structures so distant, their light hasn't had time to reach us in 13.8 billion years. Yet skepticism persists. Critics argue the flow might be an artifact of incomplete data, or that gas motions within galaxy clusters could mimic the effect. Projects like ESA's Planck satellite have since hunted for confirmation. With mixed results, some studies support the anomaly, while others suggest it fades on larger scales. Whatever the truth, the dark flow forces us to confront an electrifying possibility. The cosmic web we've mapped so meticulously might only be a stitch in something vaster. If even a fraction of the evidence holds, it hints at realms beyond cosmology's current horizon, places where the rules of space, time, and connection might be stranger than we've dared to dream. So while we trace filaments and voids within our observable universe, remember, the web's true shape might extend farther than any telescope can see, tugged by forces we're only beginning to sense. And that mystery, it's not just about where galaxies are moving, but what they're moving toward. Beneath the cosmic web's grand spectacle of galaxies and filaments lurks an even more elusive blueprint written not in light, but in particles so ghostly they pass through entire planets without a trace. These are cosmic neutrinos, the universe's ultimate spectral witnesses, left over from the Big Bang itself. While telescopes map the web's visible structure, these ancient travelers hold secrets about its hidden foundations. Born just 1 second after the universe began, neutrinos outnumber atoms by a staggering billion to 1, yet their near-weightless nature makes them nearly impossible to catch. Every second, trillions stream through your body unnoticed, relics of a time when the cosmos was hotter than the core of a star. But here's the twist, their very stealth might be the key to mapping the cosmic web's densest bones. Clusters and filaments don't just bend light, they subtly warp the paths of neutrinos too. Where dark matter and gas pile up, gravity's pull shifts the particles' trajectories, creating faint patterns in their distribution. Future observatories like the Pacific Ocean Neutrino Experiment aim to decode these distortions, essentially using neutrinos as cosmic X-rays to reveal where mass hides. It's like tracking whispers in a hurricane to map an invisible landscape. What makes this so revolutionary? Neutrinos, remember, while light from distant galaxies shows us the web as it was billions of years ago, neutrinos preserve a snapshot of the universe mere moments after its birth. Their distribution could expose how the first gravitational wells formed decades before galaxies filled them. Some theories even suggest neutrinos might have helped seed those early structures, their slight mass nudging matter into place like microscopic architects. Yet the grandest promise lies in what we haven't seen. If neutrinos cluster differently than visible matter, it could hint at entirely new physics, particles or forces shaping the web beyond gravity's grip. For now, they remain cosmic ghosts whispering a history we're just learning to hear. But one day soon, we might not just study the cosmic web. We'll read it in the ink of neutrinos written at the dawn of time. Even the cosmic web has its giants, and one dwarfs them all. Stretching an almost incomprehensible 10 billion light-years, the Hercules-Corona Borealis Great Wall isn't just a filament or a cluster. It's a galactic megalopolis so vast it defies the universe's own rulebook. To grasp its scale, picture this. If you traveled at light speed from one end to the other, you'd still need twice the age of Earth just to complete the journey. This Titan's discovery in 2013 sent shockwaves through cosmology. According to the cosmological principle, a bedrock of modern astronomy, the universe should look roughly the same in every direction at large scales. Matter ought to spread evenly like flour sifted through a cosmic sieve, but the Great Wall shatters that expectation, presenting a glaring exception, a structure so colossal it shouldn't exist under current physics. How did something this immense assemble? One theory points to the early universe's quirks. During inflation, quantum fluctuations might have planted seeds for ultra-large density variations, far beyond typical filament sizes. Gravity then amplified these anomalies over billions of years, sculpting them into a leviathan that stretches across a staggering tenth of the observable universe. Yet the real enigma isn't just its size, it's the shadow it casts on our cosmic models. If structures this vast can form, does the cosmological principle need revising? Or worse, could the Hercules-Corona Borealis Great Wall be a cosmic illusion, a trick of perspective where unrelated galaxies appear connected? Some skeptics argue it might not be a single structure at all, but a chance alignment of smaller filaments, a cosmic mirage. New telescopes like the Vera Rubin Observatory are now hunting for answers, mapping galaxy distributions with unprecedented precision. What they find could either cement the Great Wall's status as the universe's ultimate outlier, or reveal an even deeper layer of cosmic architecture we've yet to comprehend. Either way, its existence whispers a humbling truth. The universe's grandest designs might still be stranger than we dare to theorize. Imagine the universe's infancy not as a silent void, but as a boiling cauldron of sound, pressure waves rippling through a dense plasma soup. Those ancient vibrations didn't just fade into silence, they left permanent fingerprints on the cosmos, etched into the very spacing of galaxies we see today. These are Baryon acoustic oscillations, or the cosmic web's fossilized echoes, and one of the most precise measuring tapes astronomers have ever discovered. Here's how it happened. In the first few 100,000 years after the Big Bang, the universe was a searing, opaque sea of particles. Photons and baryons, ordinary matter like protons and electrons, were locked in a violent tug of war, with radiation pressure creating waves that pushed matter outward like ripples from a stone tossed in a pond. Then, as the cosmos cooled and light broke free, those ripples froze in place. The result, a predictable pattern. Galaxies today are slightly more likely to be found at specific distances from one another, like beads spaced along an invisible string. What makes BAOs revolutionary is their reliability. Unlike other cosmic yardsticks, they don't dim or evolve over time. Measure the spacing between galaxies at any era, and you're essentially hearing the same note from the early universe, a note that tells us precisely how much space has stretched. It's how astronomers confirm dark energy's grip on cosmic expansion, comparing BAO imprints from ancient galaxy maps to modern ones and finding the universe's stretch has accelerated over time. But the real magic lies in what we haven't yet decoded. BAOs might hold clues to physics beyond our current models, hints about neutrinos' masses, or even relics from before inflation. Future galaxy surveys like DAISY are mapping millions of BAO imprints, searching for subtle distortions that could reveal new forces or dimensions. So while the cosmic web's filaments and voids dazzle us with their scale, remember, its truest secrets might lie in the rhythm. A rhythm set in motion before the first stars woke, still pulsing silently through the night. The cosmic web's grand filaments should be littered with tiny galactic treasures, dwarf galaxies, the universe's smallest and most ancient star factories. According to every supercomputer simulation, these faint cosmic smudges should outnumber large galaxies like the Milky Way by at least 10 to 1. But when astronomers peer into the depths of space, they find ghost towns where bustling stellar communities ought to be. Hundreds, if not thousands, of these diminutive galaxies are missing, and their absence threatens to unravel key assumptions about dark matter and how galaxies grow. One leading explanation hides in the shadows, literally. Many predicted dwarfs might simply be too dim for our telescopes to catch. Unlike their brighter cousins, these ultra-faint galaxies could be dominated by dark matter, with just a sprinkling of stars scattered like lonely campfires in the night. The few we've discovered, like Segway 1, a galaxy with only a few hundred stars, hint at this invisible majority. Future observatories like the Vera Rubin telescope aim to hunt these phantoms down by scanning for their faint starlight against the web's glowing filaments. Yet there's another, more violent possibility. The cosmic web itself might be shredding dwarfs before they can fully form. Filaments aren't gentle environments, they're turbulent rivers of gas and gravity. As young dwarfs move through them, they could be stripped of their star-forming fuel or torn apart by tidal forces from larger galaxies. The Milky Way's own satellite galaxies show scars of such encounters, with some stretched into stellar streams that trace their tragic orbits like cosmic breadcrumbs. But the most tantalizing clue lies in dark matter's nature. If it's warmer and faster moving than current models suggest, it might resist clumping into the small-scale halos needed to birth tiny galaxies. This fuzzy dark matter could explain why dwarfs are rarer than simulations predict, and why their distribution seems oddly sparse along certain filaments. The mystery isn't just academic. Dwarf galaxies are cosmic time capsules preserving pristine conditions from the early universe. Their absence leaves gaps in our story of how the web assembled itself. Every new discovery, whether a dim dwarf finally spotted or a filament's telltale lack of them, brings us closer to rewriting the rules of dark matter and the universe's hidden architecture. So while these missing galaxies might seem like small puzzles, their answers could reshape our place in the cosmos. Picture the universe's darkest hour, a time when no stars flickered, no galaxies glowed. For nearly 100 million years after the Big Bang, space was a silent shadowland, filled only with a featureless fog of hydrogen gas. Then, somewhere along the cosmic web's earliest threads, a spark flared in the void. The first galaxies woke up, and nothing would ever be the same. Thanks to the James Webb Space Telescope, we're now witnessing this cosmic dawn like never before. JWST infrared eyes have pierced the veil of time, capturing galaxies as they existed just 400 million years after the universe began, small, fragile things burning with the blue intensity of their newborn stars. These pioneers didn't form randomly. They ignited along the densest tendrils of the young cosmic web, where dark matter's invisible scaffolding had already begun gathering gas into the universe's first neighborhoods. What's astonishing isn't just that these galaxies existed, it's how they lit up the cosmos. Their starlight didn't just brighten empty space, it ripped apart the surrounding hydrogen fog like a match held to tissue paper. Photons from those early stars ionized the gas around them, carving transparent bubbles that gradually merged, ending the so-called dark ages in a slow cosmic sunrise. This reionization wasn't instant. It unfolded over hundreds of millions of years, a patchwork of light spreading along the web's filaments until the entire universe glowed clear. But here's the twist. These fledgling galaxies weren't just passive beacons. Their explosions and outflows seeded the web with heavier elements: carbon, oxygen, silicon, the raw materials for future stars and planets. The same gravitational tugs that birthed them also shaped the web's growth, pulling more gas into filaments and setting the stage for today's grand galactic cities. The deeper mystery: some of these early galaxies are too bright, too massive for their age, challenging our models of how quickly cosmic structures could have formed. Are we seeing exotic star formation, or could dark matter have clumped differently in the universe's youth? Every new JWST discovery peels back another layer, revealing how the cosmic web didn't just host galaxies, it was forged by them. So when we trace the web's luminous threads today, we're not just mapping space, we're reading a story that began with the first starlight, written in gravity, gas, and the stubborn glow of galaxies that refuse to let the dark win. The universe's grand tapestry won't shine forever. Picture a future so distant that numbers lose meaning trillions of years from now, long after the last stars have flickered out. The cosmic web, now pulsing with galaxies and light, will stretch into a ghostly skeleton, its threads fraying as the relentless pull of dark energy drags everything apart. What was once a thriving network of superhighways will become a graveyard of isolated islands, each drifting alone in an ever-cooling void. This isn't mere speculation, it's the fate written into the cosmos itself. As galaxies exhaust their fuel and stars wink out one by one, the web's vibrant connections will fade. Even black holes, the last holdouts, will eventually evaporate over incomprehensible timescales, leaving behind nothing but a sea of scattered particles and fading radiation. Future civilizations, if any survive, would gaze into a night sky unrecognizable to us. No clusters, no filaments, just an endless dark where galaxies once danced. Yet some threads might endure. Galaxies already bound in tight clusters, like those in Laniakea, could resist isolation for billions of years longer, clinging together in gravitational defiance. And the cosmic microwave background, the faint afterglow of the Big Bang, will persist, though stretched into wavelengths so long it becomes undetectable. It's a chilling thought. The same forces that built the web will one day dissolve it, erasing even the memory of starlight. But here's the haunting question: will anything remain of the structures we see today? Supercomputer simulations hint at a possible legacy. The faintest ripples in space-time, gravitational echoes of long-dead galaxies, might still ripple outward, carrying traces of the web's architecture into eternity. If intelligent life arises anew in some distant epoch, they may piece together this lost history, reconstructing our universe's glory from whispers in the dark. So while the cosmic web's fate seems sealed, its story isn't just one of endings. It's a reminder that even in a universe destined for quiet and cold, the connections we see today, the filaments, the clusters, the vast rivers of matter, were once the scaffolding of everything. And that, in itself, is a marvel worth contemplating. Here's your next segment, crafted to flow seamlessly while introducing fresh perspectives. What if everything we see, every galaxy, every filament, even the vast cosmic web itself, isn't truly three-dimensional but an illusion? A projection, like a hologram cast from the universe's farthest edge. This isn't science fiction. It's the holographic principle, one of the most radical ideas in physics, and it might just hold the key to unraveling the cosmic web's deepest secrets. At its core, the principle suggests that all the information describing our 3D universe, every star, every atom, could be encoded on a 2D surface at the boundary of space. Think of it like a movie screen. The images appear to have depth, but they're really just flat patterns of light. If true, the web's filaments and voids might be shadows of something far stranger, a cosmic code written in the language of quantum mechanics. The roots of this idea trace back to black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, a measure of its hidden information, is proportional not to its volume but to its surface area. Decades later, string theorists like Leonard Susskind expanded this insight, proposing that the entire universe might work the same way. The implications are staggering. Gravity, the force shaping the cosmic web, could emerge from quantum interactions happening at the universe's edge. But how would this reshape our understanding of the web? For starters, it could explain why galaxies align along filaments with such eerie precision, like pixels resolving into an image when viewed from afar. Some theorists even speculate that dark matter's ghostly influence might be a side effect of this deeper projection, a flaw in the cosmic film where gravity leaks through. Yet the holographic principle remains controversial. Critics argue it's untestable, while supporters point to nascent experiments like quantum simulators that recreate holographic physics in labs as potential proof. If verified, it wouldn't just redefine the web, it would fuse Einstein's gravity with quantum mechanics, solving one of science's greatest puzzles. So the next time you marvel at a galaxy cluster or trace a filament's arc, remember, what we see might be more than meets the eye. The cosmic web could be the universe's grandest illusion, a hologram woven from the fabric of reality itself, and decoding it, that might require looking not just into space but beyond it. For nearly 2 decades, a quiet revolution has been unfolding in the deserts of New Mexico, where a modest telescope has been quietly rewriting our understanding of the universe's architecture. The Sloan Digital Sky Survey isn't just taking pictures of the night sky, it's stitching together the first real-time atlas of the cosmic web, capturing galaxies like fireflies trapped in amber across billions of light years. Each new data release adds another layer to this living map, revealing structures so vast they make superclusters look like mere specks. What makes SDSS revolutionary isn't just its scale, it's how it transforms raw numbers into a cosmic story. By measuring precise distances to millions of galaxies, astronomers can reconstruct the universe's three-dimensional skeleton in unprecedented detail. Like spelunkers mapping a cave by flashlight, each survey pass illuminates new filaments, voids, and clusters, gradually filling in the blank spaces on our cosmic charts. The latest data even reveals faint tendrils connecting massive walls, hinting at a web far more intricate than we first imagined. Yet for all we've mapped, the surprises keep coming. In 2019, SDSS uncovered a galaxy so isolated it's been dubbed the Milky Way's mirror, a lone spiral floating in a cosmic desert, challenging assumptions about where galaxies can form. Then there's the baffling dark energy dragon, a serpentine arrangement of clusters suggesting gravity might behave differently on the largest scales. Every discovery raises new questions. Are there undiscovered superstructures lurking at the survey's edge? Could voids contain hidden galaxies too faint to detect? The hunt for answers never stops. Upcoming projects like the Dark Energy Spectroscopic Instrument will work in tandem with SDSS, charting 35 million galaxies to probe the web's evolution across cosmic time. One day soon, we might hold a complete atlas of our local universe, but by then, the map will already be changing as new telescopes peer deeper into the abyss. After all, the cosmic web isn't just something we observe, it's a story we're helping to write, one galaxy at a time. Here's the concluding segment, crafted to resonate with both casual viewers and space enthusiasts while maintaining originality in every line. From the Great Wall's staggering immensity to dark matter's invisible threads, the cosmic web isn't just a structure. It's the universe's grand epic written in gravity and starlight. Every filament, every void, every galaxy cluster we've explored tells the same story, connection. Whether it's quasars illuminating ancient gas tendrils or the eerie repulsion of cosmic voids, these marvels reveal how the cosmos orchestrates its symphony across billions of years. Yet for all we've uncovered, the web's greatest gift might be its unanswered questions. Why do galactic highways align with such precision? What whispers do neutrinos carry from the universe's dawn? With tools like JWST and Euclid probing deeper than ever, we're not just observers of this tapestry, we're detectives, piecing together clues faster than the cosmos can hide them. And that's the thrill. The cosmic web isn't a relic, it's alive, evolving, daring us to dig deeper. Maybe the next breakthrough will come from a telescope's fresh data, or maybe from you staring skyward, connecting dots no one else has seen. After all, every great discovery began with wonder. So while the universe keeps spinning its webs of light and shadow, remember, you're part of the story too. Look up, the next chapter is being written